at a boundary area for the cataclastic zone or the shear zone that's marked on the maps against the rocks that at one time used to be part of the upper portion of it and now slid down through partly through erosion, partly through fault action. Now, if we're looking down and we're coming down from the skyline, we'll pan down slowly and you'll see that the rocks here on this steep slope tend not to be very rounded. They don't tend to be very tall, but they do tend to be rather flattish, almost as if they've been squeezed out and laid out to rest onto the surface of this slope. That's a good indication of the internal structure of the minerals that have been pressed and moved to realign themselves due to the pressure of this shear zone or cataclastic zone. So when the erosion occurs, the minerals, as they are breaking down, break down based off of the orientation of those minerals. And in this case, because they're laid out nearly horizontally in a line, much of the roundish effect that you would get in the undeformed rocks that we saw at Culp Valley, we're not seeing the same effect here. As we continue to pan on down, we'll go down to the bottom of this slope to a stream bed that has been created through erosion over the years. And down at the bottom there, we're going to find that that's going to be the exposed boundary between the cataclastic zone, which is going to continue underneath the darker and more rounded rocks above them or to the south. If we're looking at rocks that have been deformed through a dramatic or catastrophic action, and this happens when rocks have been impacted heavily by mass movements along a fault, or through volcanic action, or through meteorite impacts onto the ground. Well, none of those happen here, but fault action was the primary catastrophic force that forced the rocks literally onto other rocks, and that stress creates enough heat and pressure, since this is all happening underground and not in exposed air like what we're seeing here. It caused the minerals to heat up enough that they became somewhat plastic. And as they did, they realigned so that they were readjusting to the direction of stress. Stress normally is translated into rocks as 90 degrees to the angle, the direction that you're looking at in the minerals. The minerals tend to follow the pattern of running north to south, and that fits with a east to west flow of the direction of the thrust faulting action that occurred here probably about 1 million years ago. And again, underground, pushing forward westward, that stress is translated in the reorientation of the minerals here in a relatively narrow zone, but on a relatively wide basis because of the wide nature of the thrust fault as it was moving westward onto and in some parts over the existing batholith then. Look at the shape of the crystals. They're not going to be rounded or spherical in general shape, but they're going to be kind of flattened. They're flattened so that they're oriented left to right. Some of the darker minerals are also streaking left or right, as are the white-colored crystals of some of the minerals that make up this piece of granitic material that's undergone the stress of this thrust fault that pushed up and over, creating this shear zone. And if we see this, you know that you are in the cataclastic zone.